een beetje geluidsoverheid.
Hello, Gerard. How are you?
Hello.
Yeah.
I might not stay on all the time, but I'm interested in this subject.
Hey, Sravan.
Hello.
Hello.
Hello. Hi, Gerard.
Hello.
So,
I'll try to suppress background noises, so I'll have my microphone off most of the time.
Connect. Also, Bob, I forgot to ask you. We're going to live stream your talk. Is it fine for you? Or okay, thanks. I forgot to ask you. Sorry.
Is my sound okay?
Yes.
Yes, great.
and we can ask questions during the talk, Bob?
Yes, yes.
Bob?
Mhm.
Yes, that's fine.
Let me say hello to everyone. I see Bob, I see Alexei, Shrivan, Luca,
Hello, Philip.
Hello.
Rod, Irene. Hello, everybody.
No.
Michelle, Chris, and Christina. Anyone else? Oh, Branislav. Good.
Hello, everybody. I think we can wait a couple of minutes because people are just coming.
Yeah, I think it's fine to wait.
Yes, we can wait a couple minutes. Okay, maybe we can start. Hello, everybody. Today we have a pleasure to have a talk by Bob Holdom. He will tell us about ultra-Planckian scattering from a quantum field theory for gravity. Please, Bob, 1 hour.
Okay, thank you very much for having me. This talk is based on a paper having the same title as the talk. I also have a few slides from another paper which touches on some related issues. So I thought it might help to put the main idea on my very first slide. So in 3 parts, matrix elements of this perturbative theory that I'm going to be looking at satisfy something I call unitarity without positivity. But these matrix elements need not be directly physical. Now, the physical matrix elements have to involve the asymptotic states. And these matrix elements should satisfy normal unitarity. But the matrix elements of the perturbative theory may still play a central role to calculate physical matrix elements, in particular cross-sections for ultra-Planckian scattering. So all this might not be very clear now, but I hope it becomes more clear as we go along. So this slide defines the theory, quantum quadratic gravity, QQG. From the action, you see it involves the Einstein term and some curvature squared terms. The middle term is just a way to write the Weyl squared term. And I've written the action in terms of Newton's constant and masses. Now, these masses have more meaning when we look at the propagator. So in this propagator, P2 and P0 are just projection operators onto spin 2 and spin 0. And say if you use partial fractions, you'll see that this propagator describes 3 poles. So this describes 3 propagating particles. One is the massless graviton, the other is a massive spin 2 ghost, and the third is a massive spin zero, what I call gravascalar. So I'll be calling the set of these three particles graviparticles. So graviparticles will include the graviton. So this propagator and the vertices as implied by the action is basically all that's needed for on-shell tree level calculations. The propagator does have gauge-dependent parts, which I don't show because these parts do not contribute to on-shell tree level amplitudes. Now I haven't completely defined the theory because we have to make a choice of I epsilon for each of those poles. And this is what Stella showed. He showed that stability and renormalizability of the theory requires the Feynman choice at each pole. So that means the poles just take the standard form up to a minus sign, where the minus sign occurs for the ghost. Now, as for unitarity, I'll say more about that later, but let's just look for now at the optical theorem for a tree level amplitude. So in this simple relation, I've made clear the norm of the state X that we're summing over here. So that's another source of a minus sign because this norm is, of course, negative for a ghost. And on the left-hand side, you get contributions from the poles of this propagator. So there are ghost terms on both sides. And these corresponding ghost terms on the left and the right-hand sides each get a minus sign. And I think that's enough to see why the Feynman choice is needed, just to get that simple minus sign showing up on the left-hand side. Okay, so this is our first look at unitarity without positivity, and I'll come back and say more about that later. Now, this talk is about calculating tree level amplitudes, but I should say a few words about the loop effects in this theory. So for any diagram at some fixed order, it's going to have standard analytic structure because it's Feynman I epsilons everywhere. And so only the overall sign of a diagram may be unusual. Now, beta functions were calculated early, and in my notation, GMG squared is a dimensionless coupling that's asymptotically free, no matter what the matter content of the theory is. Now, more recently, there's been focus on the dress propagators of this theory. And the main thing we learned from the dress propagators is that the ghost is not an asymptotic state. And in fact, it decays backward in time. So that's very far from something that could be an asymptotic state. Now, these authors gave an analysis based on this dress propagator, which shows that the theory is unitary. So that basically goes to my point 2 in the main idea slide. That is, if you only consider physical matrix elements, then those satisfy unitarity. So as things stand, it looks then that the theory is unitary and stable, but not causal on short time scales. And by short, I mean something as short as the Planck time. Now, I'm just going to consider this to be an unusual physical property of the theory. So some analysis based on the dress propagator is fine, but it leaves open the question of how do you calculate anything? How do you use the standard perturbation theory that's based on that bare propagator that I showed earlier? Well, here I think we can learn from another UV complete quantum field theory, and that's QCD. In particular, perturbative QCD. So in that case, the perturbative states, the quarks and gluons, are also not the asymptotic states. Now, nevertheless, hard scattering cross sections are calculated for quarks and gluons. And so what does that mean? What does a cross section mean when these states never go on shell? So they cannot be directly physical. But these cross sections do form the basis for obtaining physical high energy cross sections. In fact, there's a whole industry doing this, devoted to this in perturbative QCD. So I'm raising this because the question is whether QQG may be used in a similar fashion. So here's a figure that shows the scattering of high energy protons. But before the, high energy means well above the scale of QCD. But before these protons collide as protons, you have these initial state parton showers developing, shown in green. And they're described in terms of the quarks and gluons. And then a couple of those quarks and gluons collide and generate the hard scattering. After the hard scattering, we have final state parton showers, also described in terms of quarks and gluons. These showers evolve down to these yellow blobs, which represent hadronization. And out of those come hadrons. So this whole thing represents a physical matrix element, physical particles coming in and physical particles coming out. So the partons here are the perturbative states, not the, which are the quarks and gluons in this case. And the showers occur because the partons tend to split. A parton can split into two nearly collinear partons. And that's because this process, this configuration, behaves like this in terms of the opening angle. So there's some enhancement. And then these two final partons need not be on shell, since they themselves can split. And that's how the shower continues to evolve, and the off-shellness tends to increase as the initial state parton shower evolves. Now, as for the final state parton shower, that starts with the partons far off shell, and its off-shellness tends to decrease as it evolves. So that's for QCD. What we want to consider are energies far above the Planck scale. So in that case, these graviparticles are partons, as well as any other elementary particles. So here I've listed three ways that these partons can split into two nearly collinear partons. And so with all these processes, we would have, I guess, what we can call a gravitational parton shower. So we can go back to the same figure and just relabel it a little bit. So incoming now are any two physical particles with ultra-Planckian energies. Then these initial state gravitational parton showers develop. And a few of those collide, causes the hard scattering, and then the final state gravitational parton showers. Now these yellow blobs can represent the decay of the heavy graviparticles. So after those, and as I've mentioned, the heavy ghost is actually decaying backward in time. So after these decays happen, then you end up with physical particles. So that, again, this whole thing is to represent a physical matrix element. So concentrating on this hard scattering, first of all, as I've said, it involves the perturbative states, not the asymptotic states. It represents very short time scales, tau of order 1/q. Q could be, say, some center of mass energy, or 3 momentum in the center of mass. And that tau is much less than 1 over the mass scale. In our case, in gravity, that's the Planck mass. So this is the reason why dress propagators are not needed, because on these time scales, you don't even have time to feel the effects of the dress propagator. As you saw, those effects cause the heavy graviparticles to decay, but at a later time. And the third thing about the hard scattering is that it's connected to the rest of the diagram by far off-shell propagators. So once again, it's surprising that in the QCD case, the hard scattering cross-sections are calculated as if the scattering occurs among on-shell partons. And we've just seen, well, that's not actually what's going on. So what do these cross-sections mean? Well, they have meaning if they're inclusive with respect to all the partons. Then in that case, they are in some sense dual to physical cross-sections. You're basically just using a different complete set of states to describe all possible initial and final states. So concentrating now on perturbative QQG, from that discussion, it seems that QQG need only produce sensible inclusive differential cross sections for graviparticles. Okay, now let's go back to some unusual properties of QQG, which all originate from a lack of positivity. So minus signs show up in the completeness relation whenever the state X, one of these states that we're summing over, has negative norm. It has an odd number of ghosts. So we can take this to be the definition of the so-called unit operator. And the S matrix still satisfies the S matrix unitarity relation in terms of that unit operator. So that means that probability is conserved and can sum to 1, but the individual probabilities may be negative. So in this case where we have what we could call S matrix unitarity, but at the same time negative norms, I think it's often said then that we do not have unitarity. But I think it's a little more precise to say we have unitarity in the form of S matrix unitarity, just without positivity. So that's what I'll be calling this. So let's go back to a more general looking optical theorem. Again, the norms appear, and I've also divided both sides by the norm of the I state. And then this combination on the right here is what we would have referred to as a probability in normal theories. But now the individual terms in the sum on the right-hand side can be negative. And as before, there are corresponding negative signs on the left-hand side due to the ghost propagator when you calculate this amplitude. Now, of course, you could just derive this whole thing directly in perturbation theory, just as in standard theories. Now, in standard theories, the optical theorem normally yields the unitarity bound, saying that the absolute value of any matrix element is bounded from above by some constant. And that's usually used as a powerful constraint on the behavior of amplitudes at high energies. But this derivation assumes positivity, which we don't have. It assumes there are no cancellations on the right-hand side. Well, now there are possible cancellations on the right-hand side. So let's, this ties in with some previous calculations. So these authors considered graviton scattering, and they calculated this in QQG, and they found a QQG amplitude going like Q squared at high Q. So already in this theory of QQG, we see a violation of this unitarity bound that exists in more standard theories. The other thing they saw is that the result from QQG is identical to the GR result. And I think they were aware of the fact that any tree-level amplitude involving the graviton, but not the massive graviparticles, is the same as the amplitude calculated in GR. Okay, now these other authors did consider scattering involving graviparticles. They considered graviparticle scattering off a normal scalar. And they also find Q squared amplitudes. Now they focus on that modified optical theorem that I just showed you. And they do find a leading cancellation on the right-hand side. And so I'd say maybe this is the first example of a type of cancellation that we're going to be talking about here. So we want to consider 2-to-2 scattering involving only graviparticles. So there are these 4 diagrams. 3 of these are exchange diagrams where you can exchange any of the graviparticles. And you have a 4th diagram, which is just a contact diagram. Now the Feynman rules for the vertices are a real mess. And here I give some numbers of the terms that appear in these in my computer files for these vertices. So that's for the cubic vertex, which we need, and also the quartic vertex, coming from the various terms in the action. So that's a lot of terms, and maybe this is one reason why these calculations have been slow to get done. I can say a few things about the polarization tensors. For spin 2 and spin 1, we have the two polarization states. I label them by E and O, standing for even and odd, but I don't think I need to define what those mean. Now, in the case of spin 2, if you go from the graviton to the massive ghost, these polarization tensors actually stay exactly the same. They don't depend on the mass. And the other thing to notice is how these polarization tensors can bring in extra factors of Q at large Q. So the spin 1 ones bring in a factor of Q, and the spin 0 ones, both of them, bring in a factor of Q squared. The other thing I can mention is that in the definition of a differential cross-section, there's a factor of Q over K in the center mass frame, where Q and K are the final and initial 3 momentum. So this ratio also depends on the masses of the states that are being scattered. So this is the way I calculate these amplitudes. I calculate them by contracting the polarization tensors in from the beginning. I think that makes things a little more doable. But on the other hand, we've just seen there are 8 polarization tensors, and thus potentially 4 to the 8 amplitudes to consider. Well, it's not quite so bad, because some of these amplitudes end up being the same as others, or some end up being 0. But what's clear at this stage is that the high energy behavior looks bad. We have these vertices. The terms that come from the curvature squared terms will go like Q to the 4. And then we have these other factors of Q from the polarization tensors. And so the whole thing looks like amplitudes will grow to some large power of Q. Well, I guess the reason I'm giving this talk is the fact that there are cancellations going on. And there are 2 types. One is between the 4 diagrams at the amplitude level. And another type is occurring between exclusive differential cross-sections. So this type of cancellation is not unheard of in quantum field theory. It occurs in the treatment of infrared divergences. In that case, you might wonder where did the negative contributions come in that case? Well, in that case, it comes from interference effects between terms of different order in the mod squared of an amplitude. Now, these amplitudes I'm calculating are on shell. That is, the external momenta have to be put on shell, obviously, because we're trying to get cross sections. You might wonder, well, does this really matter if I'm going to take the high energy limit? Well, it does. It's still crucial, even when taking high energy limits, because the on-shell amplitudes actually have a non-trivial dependence on the masses. So as one example of this, take a 4 graviton amplitude, which is non-vanishing, and just replace one of the gravitons by the spin 2 part of the ghost. So I've mentioned that that polarization tensor doesn't change. And so only the mass of one of the external lines changes. But in this case, that change causes the resulting amplitude to identically vanish. So that's an example of non-trivial dependence on mass. And with these non-trivial mass dependence, then cancellations are also non-trivial. So let's consider these cancellations. So let's consider an amplitude where some number of the external lines are spin 2. So then we have a choice, because each spin 2 could either be the massless graviton or the spin 2 part of the ghost. So then we have choices for the masses. The mass of each of these lines can either be 0 or mg. So that would give us 2 to the n choices if there are n spin 2 particles. So we then have a bunch of amplitudes. Let's label them by m sub i. I runs from 1 to 2 to the n. Each of these amplitudes is, of course, the sum of the 4 diagrams. And what we find is that these amplitudes end up going like q squared, or it's q squared in particular when the number of spin 2s is either 2 or 4. In other cases, the amplitude can go like q. Well, this q squared behavior is something we've already seen in other calculations. It does show that cancellations are occurring at the amplitude level, because as I just discussed before, by power counting, we would have expected at least q to the 4 and higher powers of q appearing. So cancellations are occurring, but apparently not quite sufficient, because if you take this q squared, it becomes q to the 4th in mod squares. And this does look like bad high energy behavior for those individual exclusive cross sections. So let's look at a particular example. Let's look at 4 spin 2s, all with the same E polarization. And then let's look at the whole list of distinct amplitudes which occur in this case. And so this is what I've been here. That's the whole list of distinct amplitudes. Theta is the scattering angle in the center mass frame. There's an overall factor of 8 pi g. And the leading terms are the q squared terms here. And we see even here, the coefficients are different. You might have thought they should all be the same in the high energy limit. Well, that's not true. And in fact, as I've already mentioned, some of these amplitudes are identically 0, the ones with 1 mass and 3 mass zeros. And then at next order, we have these terms that depend on theta in some non-trivial way. And so when we're interested in squaring these amplitudes, then we're going to have a q to the 4th, and then we're going to have a q squared coming from the cross term here. So let's sum over the choices of the masses and in this way get a partially inclusive differential cross-section. So I mean, let's sum things up in this way with this q over k factor that I mentioned, and then a minus sign if there are an odd number of ghosts. So this thing ends up being proportional to this partially inclusive differential cross-section. So what we find when we do this sum, first of all, that q to the 4th term, those terms all add up to 0, which is a bit surprising. Then at next order, q squared, all those cross terms I mentioned, they also add up to 0. So that was quite a surprising cancellation. So it means that all that non-trivial theta dependence I showed adds up to 0. So what's left then is q to the 0. To actually get the q to the 0 term, these amplitudes have to be expanded to order q to the minus 2 first, because there'll be a cross term between q squared and q to the minus 2 that gives a q to the 0. So doing all that, then we finally do end up with a partially inclusive differential cross-section, which in its definition has another factor of 1 over s or 1 over q squared. So that's the final behavior for this object, is 1 over q squared. And that's just like other gauge theories that we know, like QED and QCD, for the behavior of cross-sections at high energies. So what I showed you was just one example of many possible processes to consider with different choices of polarization tensors, different choices of numbers of spin 1s and spin 0s. And then there are various interchanges that I haven't shown here. Now for the spin zero ghost, I'm representing it by a 0. And in fact, we can replace any of these zeros by the S, standing for the scalar graviparticle. So we do the same kind of thing, do this sum in each case. And the amplitudes start off again being q squared or q to the 1. But after doing this sum, you end up with q0. So yeah, in going through all these cases, I always had, there's always a little suspense to see if this cancellation happened yet again. But as it turns out, it always did. Now for other amplitudes that don't have any spin 2s, then we have to rely on cancellations at the amplitude level from these 4 diagrams. So let's look at the 0, 0 to 0, 0. Remember that's the scattering of the spin 2 part, sorry, the spin 0 part of the ghost. Now this, if you just look at the contact diagram, it has a q to the 4th from the vertex, and then a q to the 8th from the 4 polarization tensors. So we expect the q to the 12th behavior of that one diagram. And the next slide, then I'm going to give that leading contribution and the various subleading contributions, just from the contact diagram. So yes, there is this q to the 12th term with some ugly theta dependence, and also depending both on ms and mg. But then you have all the subleading terms, q to the 10th, q to the 8th, all the way down to q squared. So what happens is that all those contributions at all the different orders from the contact diagram cancel with the similar contributions from the STU exchange diagrams. So that's another surprising cancellation. And in the end, you're left with q to the 0. So it's like you have to remove all this chaff before you can get down to the kernel of grain that you want. And in this case, it's a simple result here in Mandelstam variables, completely symmetric in ST and U. And notice the ratio ms over mg also doesn't appear. The other odd thing, I guess, is the double pole structure, t squared and u squared and so on. Well, that's odd, but it's not hard to understand where those come from. It's just the quartic behavior of the propagator that we started with. Now remember, all this is in the high energy limit. As you went away from the high energy limit, you would start to see the effective masses, which would come in here in various ways and affect the singular behavior that you're seeing here.
Sorry, Bob, can I ask a question?
Yes.
But just to understand, so for instance, when you consider a scattering like this one, like 0, 0 going 0, 0, just the zerolicity of the ghost, right? You are considering here.
Sorry.
The 0, 0 is the zerolicity of the spin 2 ghost.
Yes.
Okay. So when you have like the exchange diagram with a propagator, so for the internal line, are you considering the full quadratic gravity propagator?
Yes.
With the 3 poles?
Yes.
Okay. I see. Okay, thank you.
La, 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 la.
What? There's a question?
I think there is no question. Please, Bob, please continue.
Okay, thanks,
Yeah,
Bob.
that's why these amplitudes often depend on ms, the scalar mass, as well as the ghost mass. We can do the same thing with spin 1 scattering. And again, you have to strip away all the chaff and end up with this result. Here, there's a new kind of term, which is not completely symmetric between ST and U. And that's because when you interchange particles to interchange ST and U, you also have to interchange the polarization tensors. And in this case, apparently, the polarization tensors are such that the particles effectively are not identical. Okay, so in my paper, I give tables of some results. So these are the results for the various partially inclusive differential cross-sections. So they include that type of cancellation I was talking about between different exclusive cross-sections to form a partially inclusive one. And these are dimensionless things appearing because I've multiplied by an E squared. E is the center of mass energy. So in my paper, I use center of mass energy, but in this talk so far, I've been using the variable Q. But you can translate from one to the other. So each row represents a group of processes that have this spin content that I indicate here. And it also includes the various kinds of interchanges that you can make, even between interchanging the final state with the initial state. So that's all included in one of these lines. Okay, so big C and big S are the cosine and the sine of the scattering angle. And X is the ratio of MS over mg. First of all, you notice in some of these, you have a 1 over s to the 8th. And as far as X goes, X doesn't appear in any of these final results, even though, as I said, S usually appears in some of the amplitudes, but when you get to this stage, they've all canceled out. It does appear here, the X appears in these processes that explicitly have the S in the final and initial states or states. Here's another table. The daggers here say that you can replace the zeros by the S's, and the result then will just be 4 times what you see here. But then you see another kind of surprising result. If you did replace all these zeros by S's, you would find results which again don't depend on MS. And the only MS dependence shows up in these two. Now here's a table where I've listed all the processes and some properties. So the first column is this power of E before those cancellations at the level of the exclusive differential cross sections has occurred. You have this power of sine theta, like I mentioned, some of them are assigned to the -8. If you look at the residues of those singularities in theta, the theta, the -8, the residues are always positive, and for some strange reason, always a power of 2. And then finally, we can look at the value of these differential cross sections for the scattering at pi over 2. So scattering into the transverse plane. And what you see here are positive results except for 3. There's a negative result here, 1 here, and 1 down here. Okay, let me just make some comments then. So all these partially inclusive differential cross sections have good high energy behavior, all going like 1 over E squared. But a few are not positive definite, those 3. But those 3 are inelastic processes. And as you saw, the negative values are numerically small and are swamped by the positive definite elastic processes. So in particular for these elastic processes, those scatterings are strongly enhanced in the forward and backward directions. This 1 over sine to the 8th. In Mandelstam variables, it looks like that. But here again, it doesn't quite make sense to assume T and U can go to 0 because there are actually mass corrections involved here. So this expression implicitly assumes that T and U are greater than mg squared. But nevertheless, this does show us still in the high energy limit a very strong enhancement. And this result is different from TCD. It's not so strongly enhanced in this way. And so this could have implications for how these initial state parton showers actually interact with each other. So going back to this big diagram, we basically have an answer for what this hard scattering differential cross section in this black blob, how it behaves. Well, we find that it's positive and it behaves like 1 over q squared. So if you look at this diagram, it's just one big Feynman diagram. And that leads to a kind of a different picture to view things in. We could call this the off-shell picture. Yeah, so I mentioned this is one big diagram. So in principle, you could just calculate, but as I've been saying, that's not the way things are done. Things are done in the way of calculating the black blob first in an on-shell description. But let's just look at this whole big Feynman diagram all at once, and it then defines an off-shell picture. And as I mentioned, propagators closer to the black blob are getting more and more off-shell. So we have these off-shell propagators, which behave like 1 over q to the 4th. We also know there are these vertices that have extra powers of q squared, say, compared to QCD. So you have a propagator more convergent than QCD, vertices more divergent. But these two effects can tend to cancel, compete with each other. And so in this picture, it's maybe not so surprising that we can get a high energy behavior similar to QCD. So the other thing to notice in this picture, there's just no on-shell ghosts appearing anywhere. And there are no negative norms appearing anywhere. So this is what the theory is actually telling you to calculate. And we see no problems with ghosts. But to actually calculate things, we have to go over to this off-shell picture. This is what allows calculations following in the way that perturbative QCD proceeds. But in this picture, the same cancellations have to occur, but in a different way. And in this case, it's occurring between exclusive differential cross sections. And the minus signs are coming from negative norms rather than from ghost propagators. So you could say this is just a convenient way to calculate. And in this picture, there are these negative norms. And so these negative norms just act as a useful bookkeeping device for these on-shell calculations of inclusive differential cross sections. So viewed in this way, then you could view ghosts as our friends. Okay, so here are some facts. I'm trying to anticipate some questions. Okay, so you might say, well, I see some negative cross sections. They might be exclusive and inelastic, but how can any cross section be negative? Well, any negative cross section will involve ghosts in the initial or final states. But as I said more at the beginning, ghosts are not asymptotic states. So these cross sections are not directly physical. Sufficiently inclusive cross sections are positive. Another question is, well, gravitons are physical particles, so why not consider just graviton-graviton scattering? And in that case, wouldn't we be able to see a q-squared behavior? Well, in principle, yes, but I don't see how you're going to avoid these initial and final state gravitational parton showers. I don't see how you're going to avoid those when you're pumping in ultra-Planckian energies into this scattering. And the third question, do the cancellations occurring between exclusive differential cross sections carry over to cancellations in the sum over states in the optical theorem? Well, typically not, since the sum in the optical theorem just corresponds to sum over final states, while our cancellations involve a sum both over the initial and final states. Okay, so before we going on to those few slides from that other paper, maybe this would be a good time to stop for any other questions.
Yes, I have some questions.
Please, please ask a question. Yes, Philip.
Bob, I'm a little bit puzzled about this.
Unitarity, though we usually think in terms of SS dagger is one, is really a statement about the completeness of the states of the Hilbert space. And what you have, if you're working with these negative norm states, is that the positive norm plus the negative norm combined is complete. And that's why earlier on you were able to say you can have unitarity without positivity. It's because the whole thing is complete. But then I'm puzzled, if the ghost states somehow disappear, you're trying to say that the asymptotic states are only positive norm and yet they're still complete. And that's the thing that puzzles me. Now, in QCD and confinement, I would have said, okay, the quarks and the gluons all disappear from the asymptotic states and they contain color singlets. But somehow you want to keep the positive norm graviton in your asymptotic states and get the negative norm ghost to not be in the asymptotic states. And that's sort of not quite the QCD picture.
In the sense that not all the graviparticles are not asymptotic states?
Yes. They're not, somehow you've got to find the analog of the color singlets.
Well, the physical states here are the analogs of the hadrons, yes, the colored singlets. So in the high energy scattering, which is done in terms of the degrees of freedom of the asymptotically free theory, there are these both positive and negative norm states. And yeah, as you say, that is a complete set of states. So at that level, the ghosts are not disappearing. They're playing an essential role in calculating things at very high energies. But maybe your question goes more to the question of how do I know this theory is actually just unitary if I only consider asymptotic states? I referred to that paper by Donahue and Menendez. So that's their claim, that if you do just consider the asymptotic states, then they argue that the theory actually is unitary.
Well, as long as the asymptotic states are still complete, then of course I'll agree. But I'm puzzled that they could be. That's my question.
Yes, I guess that's a fair question. We would have to look closer at what they did, I guess.
Okay.
Another way to see what's going on is to take one of my initial or final states in this ultra Planckian scattering. So, and then just say that in the initial state, and then just evolve that state forward. So that state then ends up being described by these far off shell degrees of freedom in the perturbative theory. So that gives you a direct correspondence between what a physical state is and these far off shell excitations that occur close to the scattering. So that's just a unitary evolution. And then we just play the same trick as done in perturbative QCD and say, well, we don't want to deal with all that off shell mess. We want to just calculate things as if things are on shell. And we just do that by saying again that the perturbative theory gives us a complete set of states.
May I ask a question?
Yes?
In QCD, the complexity of these Feynman diagrams comes about because you have running coupling constants, which are dimensionless in principle, but can run to large values logarithmically. Now, which parameters in your theory are dimensionless and run to large values? I have the impression that with these graviton-like heavy particles, you can arrange everything to have only small coupling constants. And then, of course, comparison to QCD is unnecessary.
Well, I did mention a coupling in my notation was Newton's times mg squared, the ghost mass squared. So that is a dimensionless coupling. And that's the coupling that was shown early on to be asymptotically free. So that's the analog of the running of the coupling in QCD. And in this case, also that running can cause that coupling to get large. In fact, there's a different way we could believe this theory is actually defined at the fundamental level, is to have no Einstein term and just take advantage of this running, just as in QCD. And where the coupling grows strong, then you would expect the Einstein term to be dynamically generated. So in that type of picture, I think it's getting very close to QCD. But
I
as
believe
far
it's actually the Higgs theory with which this resembles. In the Higgs theory, of course, you have the Higgs self-coupling, which has a quadratic and a quartic term. And at low energies, the quadratic terms are important, but at very high energies, only the quartic term. So that so that the Higgs mechanism disappears at very high energies. And something similar might be happening here with these graviton particles.
yeah, in the sense that the curvature squared terms are the ones that do dominate at extremely high energies.
Exactly, but I don't see why that would become non-perturbative.
Well, do you agree that the Weil squared term has a coupling which is asymptotically free?
Okay. I have some other comments, if I may. One is that with a theory as elementary as the gravitational field theory, would it be important to consider very carefully the arguments about the interpretation of quantum mechanics? I know most people don't like to think about it, but actually there are ways to blame some of the diseases that you see to actually a property of quantum mechanics itself. For instance, these very heavy particles you talk about could have such high energy levels that a system, any ordinary system that has ever been studied today in experiments, never reached those energies of the separation of the energies of the one ghost state and the zero ghost state. Those energies are too big. Whether they go to positive or negative infinity doesn't really matter. You can't excite those states. And instead what those states do is they generate quantum mechanical interference in a way which seems very interesting to me. I have another comment, and that is that one particular place where you can study the effects of very highly energetic particles very closely is at the horizon of a black hole. If you try to quantize a black hole, you want to get something decent out of your theory. But at the horizon, particle scattering, ingoing particles scatter against outgoing particles at energies much bigger than the Planck scale. However, there you see something marvelous happening, which is you can transform away one of them. You can either transform away all the ingoing particles or transform away all the outgoing particles. It's something I call a firewall transformation, so that there's no firewall. So one difficulty of black holes then disappears. But also you never need to consider particles that collide against each other at the center of mass energy beyond the Planck's mass. That would simply not be necessary to consider. In fact, you can transform all that away in a theory which looks much more decent at very small distance scales. There's still also things which are not understood, of course. But
okay.
My comment is one has to take such different features into account to get a more complete theory of quantum gravity.
Okay, but you see that in what I'm talking about, a whole new perturbative regime is opening up that we've never really even considered before, above the Planck mass.
Yeah, but you know very little about the basis of the theory beyond the Planck mass. For instance, it's very likely that space and time form a lattice there. One can actually calculate the lattice parameter, which is a fixed number in terms of the Newton's constant. Then, of course, it is very hard to even consider what it means when particles collide with energies at the center of mass energy. bigger than the Planck mass. That may never be necessary to consider, because by that time, the laws of physics have completely changed when you reach that domain. That's, well, you may just ignore that. That's just the opinion I have, the way how we have to think about theories, which first of all must be very complete. I'm unhappy with theories that depend on the kind of chaos as it occurs in QCD. Because QCD is a theory which was could very well be studied experimentally so that we can avoid making mistakes. We don't have such luck in quantum gravity. We have no experimental data about beyond Planckian scale scattering. So what we are doing may or may not be complete nonsense. We don't know.
Yes, but I think the idea that quantum gravity is just an ordinary quantum field theory. Well, as we see here, it's not completely ordinary quantum field theory. But that idea must have been maybe the first idea for quantum gravity, right? Why not make quantum gravity like everything else? And that was dismissed, or ran into problems very early on. And so for many decades, we've had to think things in completely different ways. So it's possible that we didn't think deeply enough at the beginning about this possible quantum field theory for gravity.
Okay. Well, here I agree that we have to think about all possibilities, and if you find a way to deal with beyond Planckian scale physics in terms of quantum field theories, fine. But I have reasons to suspect that nature is smarter than this. But anyway, it's a nice attempt.
Okay.
Okay, where is one more question? Ralph, please ask your question.
Hello, hi, very nice talk. Can I ask some basic questions about quadratic quantum gravity? So for example, like in quantum gravity, I would have this Hamiltonian constraint. So it looks like this is like a field theory kind of quantum gravity. Should I only consider those states which satisfies the Hamiltonian constraint in some sense in quadratic quantum gravity?
Well, I guess I'm treating this whole theory as just defined by a path integral, and defining the I epsilons that appear at the poles. Then I think that's a full definition of how to do perturbation theory in this theory, and that's all I can relate to at the moment.
Okay. Another tangential question: is there any notion of holography over here? Because in a theory of quantum gravity, I would expect it to be a holographic theory, right?
Well, this is part of my other work that I think about is when you look at this theory as a classical theory and just look at possible new solutions, there are possible replacements to the whole black hole picture. And if you look at those solutions in certain ways, maybe you can see some remnant of the picture you're talking about. But I'm talking about solutions that have no horizon. It gets to a configuration that is extremely close to having a horizon, but it doesn't. So in that sense, it might be getting extremely close to the picture you're talking about too.
Okay, thank you.
More questions, please.
Is Bob going to continue a bit more? If so, I'll ask a question at the end.
Okay,
Yeah.
okay.
Now let me just continue, because this maybe brings up because as people have been saying, why are we even interested in ultra Planckian scattering? It's never anything we'll ever check. So it's just a question in principle, is there such a theory that could explain something up in those energies? But a more interesting question is, does any of this UV complete theory give things at low energies that we could check? So the first question could be, does it affect the scattering of gravitons at low energies? Well, no, and we've already said that QQG gives the same graviton scattering amplitudes as in GR. But QQG does give corrections to the scattering of matter. So in this other paper, I looked at photon-photon scattering. And that means these diagrams where, again, you exchange all the graviparticles in each of these diagrams. So in this case, things are easier, and we can just write down a result that's valid at all energies that's induced by QQG. And now you can start to see how the masses can enter and affect these kinds of expressions, where in the high energy limit I was considering before, we didn't have these masses downstairs like this. But in any case, it gives a 1 over S at high energies. It matches the GR scattering of photons at very low energies. Once again, there's no dependence on MS. And as I just said, the poles are altered because of MG. So the context in which people usually talk about corrections at low energies is at, say, the effective field theory or the amplitude level. So let's consider an amplitude where, again, all the polarizations are the same. These are the photon polarizations now. So that's what it looks like. And let's try to extract the UV contribution to something. So that something will be the forward scattering amplitude. So to get this thing we want, we take this amplitude, we subtract off the GR piece, then take t equals 0. And so then that'll be the UV contribution to the forward scattering amplitude. And that's what it is. And we're interested in low energies, so it takes S small. And we get this minus S squared term. And the main point is that it's minus. So the low energy correction is negative, and it's a direct consequence of the lack of positivity of QQG. And so it's showing us that these ghosts that have little to do with initial or final states, but it shows that these virtual ghosts do have physical effects, and they show up like this. Now, in this case, this negative sign in this forward scattering amplitude apparently is a sign of superluminal propagation. On the other hand, this correction goes to 0 as m Planck goes to infinity. And if I understand what these authors are saying, that they call this a decoupling case, and they would say apparently that this might even be impossible to detect. And one last thing I'll mention is the Froissart bound. So let's take that same amplitude and go the other direction to high S. And this is the result, and then let's expand in small t. The first term is the standard T-channel pole of gravity. But the second term is interesting. It's a minus S squared term again. And that term by itself would show that the Froissart bound is not satisfied. And we can see exactly why. This term is just coming from expanding the 1 over t minus mg squared. So it's just coming from the fact that there's a ghost exchange in the T-channel. So yes, the Froissart bound is not satisfied in this UV complete theory of gravity, but it causes no problem because we do have a UV complete theory. So whatever we want to know about the theory, we know. We don't need some bound like this. So yeah, this bound is often hoped to be true in gravity to be able to make statements when the UV completion is unknown. And I think we see here that QQG shows how easy this bound can be violated in a UV complete theory. Okay.
Excuse me, may I interrupt you with a short question?
Yeah.
I just want to clarify this point. So are you saying that you do not really, how to say, want Froissart bound as long as you believe your theory is UV complete? Is it what you are saying?
Well, we have a give you complete theory, and then we can just ask, is the bound satisfied? And we find no, it's not satisfied. But I have
And
one more.
isn't it a manifestation of non-locality that you do not have Bifrost are bound?
I don't think so. It's a local quantum field theory.
Okay.
And it's just showing how easy a T-channel exchange of a massive particle is going to generate a violation of the bound.
Okay, I see. Thank you.
I have this last slide. I think I'll just leave it here, though. This slide illustrates the type of things people do on the complex plane, trying to make use of for example, the Froissart bound. But here, we can calculate whatever we want about any amplitude because we know exactly what's going on at infinite energy. And in this particular table here, there's a pole at infinity. And we can calculate the residue of that pole at infinity. So we know everything. But I think I'll just leave it like that. If people want to ask more, they can. So yeah, thank you.
Okay, thank you very much. Thank you very much. Questions, please? I see questions from Philip. Philip, please ask your question.
Yes, Bob. First of all, thank you again, Bob, for the presentation. I mean, as you know, Carl Bender and I have a completely different understanding of the fourth order theories. And our argument is that the norm, that you should not be using the Dirac norm, but you should use the overlap of a state with its CPT conjugate, and that one's positive. But let me try to connect that to what you've been saying. There was an earlier question about whether you can formulate the entire thing as a path integral. And what Carl and I found was that one, in order to get the path integral to exist at all, you do need the I epsilon prescription that you've been using. That's otherwise the integral already diverges. But two, you need to continue the fields in the measure into the complex plane in order for the integral to exist. And that basically boils down to telling you that the quantum theory is not one with a Dirac norm. But the question for you is, what's the domain for the theory that you're looking at for which the path integral actually exists?
Well, I'm just using it in the form of a perturbative expansion. And so I'm not sure I'm seeing the type of problems you're talking about.
Well, that's what we did. I mean, we actually worked it out in some detail to discover that it did not exist on the real axis.
So how does that translate into the perturbative expansion?
Oh, what it basically says is if the path integral exists with real fields, then the underlying theory is the standard Hermitian theory, and the perturbation theory matches the path integral expansion. If the path integral has to be continued into the complex plane in order to exist, then the underlying theory, the underlying quantum theory, is not a Hermitian theory.
Yes, but how does it translate into the perturbative theory? Like what things?
Okay, what we did was we first of all quantized the free fourth order theory, just the lowest order, and then the path integral will be the expansion in powers of the coupling constant. Yeah, that's we did it. We showed that the perturbative piece already had to be continued into the complex plane.
I know. So you're telling me something should be going wrong with what I'm doing. So
well, let me put it this way: if you're going to work in a Hilbert space with negative norms, something should go wrong. And what you showed right at the end was you got that negative correction to Newton's law. But what I believe the content of your talk is that at ultra Planck scales, these problems are not relevant. which is of course is a very interesting result. And by the way, I think that's the content of the paper of Hawking and Hertog.
So yes, I agree with what you're saying, because if you do take this theory at face value, yeah, then it's the standard theory that has negative norms, and negative norms have various problems. But I think the point of this talk is to show that how I'm using this theory is not on face value. I'm using it in a very particular way to calculate very high energy cross sections. So it's hiding behind the region where these scattering particles have become very off-shell, very high energy. Sorry?
What was that?
So yeah, I'm using it in a very particular sense where the theory doesn't have to do everything properly, because in this context, all it really has to do is produce inclusive differential cross sections. That's all it has to do.
Mm-hmm.
And it seems to be enough to do what you need it to do.
No, I agree that a theory with a disease doesn't have to be diseased everywhere.
Yeah.
If I may ask,
that's the question I'm raising. Can we take this apparently disease theory and find that it's actually enough to do what it's supposed to do and no more?
Okay.
That's the question. Yes.
One further question, if I may. You mentioned earlier on that the ghosts aren't in the asymptotic states because they decay.
Yes.
What do they decay into?
Normal positive energy particles, because that's all we have. This theory is stable, like I said at the beginning, so everything has positive energy, and that's what the ghost decays into.
Okay.
Okay. I see a question from Alexei Koshelev. Alexei, please ask your question.
Yes, thank you. Actually, I will continue on the same buzz about this minus sign, and I think recently, indeed, it attracted also my attention and attention of my collaborator, Anna Tokareva. And I can say that in principle, we just recently put some paper with her and with also Mario Herrera, and it was shown there that in principle, it's indeed maybe possible even without talking about ghosts, that this minus sign can be consistent as long as you examine more carefully Laplace transform and properties of the real part of the amplitude. So in principle, generically, it also doesn't need to definitely spoil the Froissart bound. But what is important that it relies on the examination of the real part of the scattering amplitude, which we did in the paper. And let's say like this, it may be possible that you can achieve the same minus sign and explain it without going, for example, to ghosts or stuff like this. So I would not really worry about this minus sign as long as I believe in what we have computed now paper.
Yes, that's a good point. And I saw your work, and there's some other work also, I think, saying something similar, that this negative sign, at least at some level, may be fairly natural.
Yeah, because the point is that when you examine, for example, the optical theorem, you usually concentrate on the imaginary part of the amplitude, but also there is a real part, which, as long as it's accounted, there is no too much of limitation what you can do there, and it's not like granted that you can give that, can get this minus contribution, but it's not excluded by any general statements from just Laplace transform, which you use to, which you utilize to obtain, to restore IR part from UV behavior. The only thing we did in our analysis, but it was not obligatory, we did take Regge behavior at the, for the amplitude in order to specify a little bit what we are talking about. But it also was not really necessary. It was just to simplify the computations and create the showcase.
Okay.
Okay, thank you.
More questions, please.
It's not a question, just a comment on what Alexei said, which I find
Okay.
interesting actually. But usually, when people work with this effective field theory, positivity bounds, and so on, for massive particle, they can use the Flusser bound, and in the end, they get, for instance, that the second derivative of the amplitude in the t=0 limit should be positive. But if the energy theory has massless particle like gravity with gravitons, then the second derivative of the amplitude in the should not, I mean, doesn't need to be positive. And from also Alexei paper, the conclusion was basically that A double prime, so sorry, M double prime should not be positive, should not be expected to be positive from a UV completion of general relativity. And actually, what you are finding is that somehow this UV completion, indeed, that you are considering does not satisfy A double prime positive because you have this minus sign. So it's really consistent with this expectation also from some IR point of view. And yeah, I mean, I find it very interesting.
Okay.
So I mean, it's not this minus 1/2 S square over mg square is not worrying, I think. It's somehow expected.
Okay.
Okay. More questions? Okay. Dimitro, please ask your question.
Thank you very much. I have a comment and a question. So this is related to a comment by Professor Gerardo Stuft about scattering, 50 scattering above the Planck scale. So if I take purely effective field theory point of view, eventually I could think of Planck scale as a scale where a new symmetry is restored. And that would be scale symmetry, or more exactly, would be a local scale symmetry, or for example, would be gauge scale symmetry, as it happens in Weil conformal geometry, in the original theory by Weil. In that formulation, in that setting of Weil geometry, one can write down quadratic gravity Lagrangian, which is something like r squared plus c squared plus f squared, where r is scalar curvature but in bigeometry, c squared is a bitensor squared but in bigeometry, and f squared is the length curvature tensor, so to say, or the kinetic term of the Weil vector, the gauge field of the scale symmetry. So in that sense, I think that would be, for example, a setting if such a symmetry is broken at Planck scale. In principle, I see no reason why one cannot use an effective field theory approach and say, look, above this Planck scale, the new symmetry is restored. So I'm perfectly entitled to do an effective field theory approach. So my question is whether have you thought about doing quadratic gravity in such a setting, like the original Weil geometry, rather than in Riemannian quadratic gravity, so to say, because they are obviously related one to the other, except that in Weil geometry we have this additional symmetry, which is the gauged scale symmetry, which is the symmetry of the connection. Weil connection. In Riemannian case is not a symmetry of the Levi-Civita connection, obviously. And that's where I would think that some of the problems lie with scattering above the Planck scale. So, would you please comment on that, or whether you can think of doing quadratic gravity in Weil geometry rather than Riemannian case?
Well, do you still have the negative norm ghost in here?
Well, you still have the cost from a c-squared term, because c-squared in Weil geometry is c-squared of Riemannian geometry plus f-squared, where f is the field strength of the Weil vector of gauge dilatation.
And how do you think about that problem with a negative norm?
Well, I haven't thought, but I'm taking just the pure field theory point of view, thinking that about the Planck scale you restore the symmetry. So there is additional, there must be additional degree of freedom. So there is this Weil vector of the symmetry, which obviously would have to be taken into account in the scattering processes. The gauge field of scale symmetry. Or Weil used to call it Weil photon, but of course it was not a photon. It's a Weil vector of gauge dilatation, the space-time symmetry.
Okay, so it sounds like it could be an alternative choice for the UV theory.
Right, because, sorry.
I mean, the choice I've made is just as close as you can get to the QCD theory. So there is a kind of a scale symmetry appearing in the far UV, but it's broken by the running of the coupling. And so that breaking just gets stronger and stronger. So you can talk about dimensional transmutation. And but I guess in your case, could you also talk about the Einstein term being generated when the symmetry breaks?
Yes, I mean that's the whole point.
Yes.
You do generate the Einstein term because this Weil gauge symmetry, let's call it like this gauge scale symmetry, is broken spontaneously to, if I take just r squared in Weil geometry, this is broken to Einstein term plus the Weil vector field becomes massive so Stuckenberg by eating the spin zero mode propagated by r squared.
Okay.
So you are left with the Einstein term plus the cosmological constant, which is positive actually, plus the Proca field for the Weil vector field. And on top you have c squared term.
Okay, but I'm just saying that QCD also generates a mass scale without putting it by hand. So you don't need a symmetry in the UV to get the generation of a mass scale like QCD generates it.
I agree. I fully agree. No, my point of view was mostly about physics, about Planck scale, and whether you thought for that part of the talk. No, I fully agree with what you said, of course, regarding the QCD part. I mean, that's a separate. But I'm thinking for the UV part about the Planck scale scattering. I think that would change in this picture.
Okay. It would be interesting just to recalculate some of the things I've calculated to see how things change.
Yeah, that's why I'm asking you. Have you thought, or do you think it would be worth doing that calculation, at least for some simple setting? I mean, for some simple amplitude, because obviously this is very technical, so one should make sure it's worth the effort beforehand. But again, what I want to emphasize is a symmetry that one restores about the Planck scale, which can change completely the UV behavior, because in a sense it's like a gauge gravity. We have a gauge principle behind which generates the Einstein gravity. And this symmetry is important because it would prevent me from having higher dimensional terms in the scattering, because there is no scale well above the Planck scale to suppress them. Where I have the full gauged scale symmetry, I cannot write r to the 4th. I can only write r squared, c squared, and f squared, where f is the Weil vector field strength. So the UV behavior is much better behaved than saying that what we have in Riemannian case. In a sense, what I'm trying to say is that Riemannian gravity, quadratic gravity, is a bit like a gauge fixed version of Weyl quadratic gravity. Because the moment you break it spontaneously, the symmetry by Stuckenberg, Weyl quadratic gravity in conformal geometry becomes quadratic gravity in Riemannian geometry without the symmetry.
So your theory is, sorry, there's some kind of echo. It's hard. So your theory is a renormalizable theory in asymptotic control?
It's a good question. In 2019 at the Scaling Variance Conference at CERN, I think I asked Professor Philop-Stelle about renormalizability, and he said as long as the theory only have on top of a massive vector boson of gauge dilatations, which becomes massive by Stuckenberg, and is anomaly free, which is very interesting, then there is no reason to think that it cannot be renormalizable. Power counting is, of course, by power counting is renormalized. So in that sense, I don't see a problem in that sense. I don't claim it's renormalizable, but by power counting, obviously, yes. And there is only one Weyl vector, gauge dilatation, which becomes massive by Stuckenberg. That doesn't affect renormalizability, spontaneous breaking.
Okay.
Okay. Anyway, so maybe I can send you a reference, and I want to ask you more about this, how to do similar calculation by quadratic gravity setup.
Okay.
Thank you very much.
More questions, please? Okay, I don't see more questions. Okay, let's thank the speaker once again. Bob, thank you very much for your very interesting talk. Thank you all people who participate in the discussion. So thank you very much. Bye-bye.
Thank you, Bob. Thank you.
Thank you very much, Bob.
Thank you very much. And
Thank you very much, Bob.
send your slides.
Yeah, if you can send me the
It would be great to
slide.
upload them to the website.
Yes.
Okay.
Yes, thank you.
Thank you very much.
In fact, you have a great slides. Yes, very well organized and very well presentation. Yes, very well. Thank you.
Bye.
Thank you, Bob. Bye-bye.
Bye-bye.
Thank you.
Alexei, please don't forget to check the data of your visit. Yes?
Yeah,
Okay, thank you. Bye.